In this lecture here, we want to now start talking about points of inflection. So in the previous lecture, what we did was we were talking about concavity, all right? So intervals where functions are either concave upward or concave downward. And so what we're going to see here, these points of inflection, it's where the concavity changes for a function. Okay, so where concavity changes. So that means it goes from being concave upward to concave downward, or concave downward to concave upward. All right, so here's the definition. Let's let f be a function that is continuous on an open interval, and let's let c be a point in that interval. All right, if the graph of f has a tangent line, all right, at the point c, f of c, then that point, that tangent line point, is a point of inflection of the graph when the concavity of f changes from upward to downward or downward to upward. That's all, just the concavity changes. So like going back here for, let's just say this example here, when we worked at this one in the previous lecture, how it changes from upward, concave upward to downward, there's a point of inflection here at x is equal to 0. And where it goes from downward to upward, there's an inflection point here at x is equal to 3/2 for this function here. Just where the concavity changes. All right, so what are exactly then how we talk about how you find points of inflection? So if c, f of c is a point of inflection of the graph of f, then here's what needs to happen. Either f double prime, the second derivative evaluated at c, has to be equal to 0, or f double prime of c does not exist. Okay, so just like what we saw when the first derivative evaluated at c is equal to 0, it was a relative extrema. Here, when the second derivative evaluated at c is equal to 0, we have a point of inflection. Note, I just wanted to do this. It is possible for the second derivative to be equal to 0 at the point, and that it is not a point of inflection. And I'm going to do an example of that and show you. Okay, so I've got two examples worked of this. And it's going to follow a lot of the previous problems. What we're going to do is we're going to rework concavity. We're going to talk about, the intervals where it's concave upward, concave downward, because we're going to check where it changes. So we're going to need to set up these type of tables again. Okay. So let me show you a visual of this, before we jump into our examples here. So we're talking about this point of inflection is a point where the function changes from being concave upward or concave downward. And so this visual here is going to show this. So the blue line here, okay, is the tangent line. And now look, this right here, I'm saying this point here, okay, for the function below, the function is the red graph, okay, so this is the function f of x, okay. This point, 1, -1 is a point of inflection, because watch what happens to the slope of the tangent line here. Okay, it's falling, 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 so it's concave downward, and then as soon as it hits this point, the slope of the tangent line starts rising, so it goes concave upward. So it's concave downward over here, concave upward over here, and where that changed right there, how it's starting to rise now, okay, that's that point of inflection right there. All right, so let's find these on the graph, and even one of them I'll show you on the graphing calculator. All right, so the first one here is going to be a trig problem, and I put the unit circle up there. So for the following, all right, we want to find the points of inflection and discuss the concavity of the graph of the function. So here's going to be the function. Let's look at f of x is equal to cosine of x over 2, and let's just look on the interval 0 to 4 pi here. Okay, so here's what we know. We need to find concavity and points of inflection. So this example is going to focus on the second derivative. So we'll start by finding the first derivative, f prime of x. So the derivative of cosine is minus sine, x over 2, and then the derivative of the inside of the function here is 1/2. Okay, so this is -1/2 sine of x over 2. So then we take the derivative of this. So f double prime of x here, all right, that's going to be -1/2. Derivative of sine is cosine of x, or cosine here of x over 2, and then the derivative of the inside, again, is 1/2. Okay, so the second derivative here, 1/2, 1/2, is -1/4 cosine x over 2. All right, so here's what we need to do now, okay? Just like we did before, we need to set f double prime of x equal to 0 and solve. So we're going to have minus 1/4 cosine of x over 2. That's going to be equal to 0. So the minus 1/4 doesn't matter here. You can divide it over. You get when does cosine of x over 2 equal 0? All right, well, let's look when cosine equals 0, right? Cosine equals 0 at pi over 2 and 3 pi over 2. Well, we have the 2 over here. So this is going to happen then when x is equal to pi, because when you plug in pi, you'll get pi over 2. And then it's going to happen at 3 pi. Right, because when you plug in 3 pi, you'll get 3 pi divided by 2. Boom, you get 0. All right, so look, my points of inflection, they can occur. They can occur at when x is equal to pi or x is equal to 3 pi. All right, so what we have to do here now is set up the table and find those intervals of concavity and see where they change. All right, so I'm going to bring that to the next slide here. All right, so our original function was this. F of x was equal to cosine of x over 2. And we were just looking on 0 to 4 pi. And our second derivative ended up being minus 1/4 cosine of x over 2. All right, so again, set up our interval. So the first interval is going to go from 0 to pi, right? Because going back, that was one of our first values. Then it's going to go pi to 3 pi. And then that last interval is going to go from 3 pi to 4 pi. All right, so now what we need to do is we need to pick some test values. So look, an easy one between 0 and pi would be pi over 2. Here, I'm going to pick 2 pi. And then over here, what I'm going to do, and basically it needs to be between 3 and 4, so it's going to be 3.5 pi, which is 7 pi over 2. All right, now let's look at the sign of f double prime. So what is f double prime of pi over 2? Well, when you plug pi over 2, you get cosine of pi over 4. Well, look, pi over 4 cosine, that's square root of 2 over 2, and then times negative 1/4. So that's less than 0. F double prime of 2 pi. Well, that ends up being cosine of just pi, which is negative 1. Negative times negative here, that's positive. And then f double prime of 7 pi over 2. Well, when you plug 7 pi over 2 here, you get 7 pi over 4, which is positive, but then you're multiplying it by a negative here, so that's less than 0. So our conclusion here, it's downward on this interval, concave downward, and then here it's concave upward. Nice. And then here, over here, it's negative, so now it's concave downward. So then let's just talk about concavity first, all right, and then we'll talk about the points of inflection. All right, so it's concave downward on 0 to pi, and then also from 3 pi to 4 pi. And then it's concave upward on this pi to 3 pi. All right, now here's the great thing. It has 2 points of inflection. 2 points. Look, at pi here, it's changing from concave downward to concave upward. So it has a point of inflection at this pi comma f of pi. All right, well, look, you got to go back here, right? So I've got to plug pi into this. Okay, so what is cosine of pi over 2? You know, if you need to go back here, cosine of pi over 2, right here. I'm sorry, I made a little no, I'm sorry, got a mistake there. Pi over 2 here gets you cosine of pi over 2, gets you 0. So this is the point pi 0. Sorry about that little slip up there. And then another point of inflection and then it's going to occur at 3 pi, f of 3 pi. Well, this is 3 pi, and then when you plug 3 pi, you get 3 pi over 2, which is right here, and that's cosine of 0. Cosine equals 0, excuse me. So these are my points of inflection there. So you look where they turn, right? So it goes from upward to downward. So that's where I get the 3 pi. Downward to upward, that's where I got that pi. Okay, let's get away from a trig one, and now let's do a polynomial one. And what's going to be really interesting about this one is going back. Notice how I said sometimes it's possible for the second derivative to equal 0 at the point and not be a point of inflection. All right, so we got a trig one out of the way. Even sometimes your professor stumbles there a little bit, remembering with the unit circle, so have that handy. And then let's have this one, okay? So let's look at this. F of x is equal to 4 minus 2x to the 4th. Now just looking at this as a polynomial function, so the domain is negative infinity to infinity. All right, so points of inflection, concavity. Got to find the second derivative. So the first derivative, this ends up being before it goes away, so this ends up just being minus 8x cubed. And then the derivative of that, so the second derivative, ends up being minus 12x squared, or excuse me, minus 24x squared. Sorry about that. Okay, so what you're going to do is, again, you're going to set this equal to 0. And you're going to solve. So you have f double prime of x is equal to minus 24x squared. So you're going to notice that only happens when x is equal to 0. So you only have one possible point of inflection here. Okay, so you're going to have to go from negative infinity to 0, 0 to infinity. So set up your interval. Negative infinity to 0, and then it's going to be 0 to infinity. You're going to pick a test value. So I'm going to pick -1, and over here I'll pick 1. And so now look, you're looking at the sign of the second derivative. Well, f double prime of -1. Well, look, it's x squared, so that's always positive times -24. So that's less than 0. And it's the same thing over here. F double prime of 1 is also less than 0, because 1 squared is 1, but times -24. All right, so what's my conclusion? Well, look, it's concave downward from negative infinity to 0. And then it's also concave downward from 0 to infinity. So notice how it doesn't change, like the concavity doesn't change here. All right, so you can just say right off the bat it's concave downward on negative infinity to 0, and then also on 0 to infinity. And then there are no points of inflection here. So even though the second derivative was equal to 0, there were still no points of inflection. And look, let me show you the graphing calculator for this. And if you see here, the slope of the tangent line is always going to be falling. It's always going to be falling. So as you go left to right, the slope, it's always falling. So in this case here, it's okay for the second derivative to be equal to 0, but that doesn't necessarily mean there is a point of inflection. All right, class, I'm going to follow this lecture up with talking about the second derivative test to end this section. And this was 2 quick examples, but you can see here it still centers around concavity, and we did a bunch of examples of those. And so you'll get to practice this again, obviously, in your homework.